And so
So the keyboard's here.
keyboards here. Great. Okay, great. Okay, great. So I should just jump in?
Yep.
Everybody can hear me, right? I don't need a mic or anything?
You need a mic
You
for
should
the
use
live
the
stream.
mic for the live stream.
This thing?
One right in front of you, yeah.
There's like two glued together.
the
Six
top
glued mics. Okay, great. Hi everyone. So yeah, we're going to be discussing oracles. I think first, usually I like to create some shared context about the significance of oracles, which I think the vast majority of you have. So I'll kind of just blow through that. And then we'll look at our approach in terms of decentralization, how oracles make binding commitments to smart contracts, and then how we use multiple approaches in conjunction with decentralization, like trusted execution environments. So generally speaking, I think everybody's aware of the problem. Smart contracts can't speak with the data they need to expand. Fundamentally, this affects, in our opinion, the majority of contracts. And this problem basically keeps Ethereum from scaling into more useful use cases. So it's not necessarily the scalability of Ethereum on the level of its own transactions. It's more the scalability of Ethereum to be useful for the majority of use cases, the ones beyond token movement. Fundamentally, I think what we'll see when we have working oracles is a similar shift like the one we've seen historically. So we saw a shift from Bitcoin multi-signature as the only smart contract into protocol smart contracts in 2013 and 14. That's when a lot of us got into the space. That's when I got involved when we started building the very first smart contracts, because this new capability to use various types of smart contracts emerged. Then Ethereum did a very good job of taking us from these protocol-based smart contracts to scriptable contracts. That expansion in capabilities for developers created the large explosion in value we've seen over the past year and a half, 2 years. And we think the next iteration, which logically makes sense, is that as you expand the features, now all of a sudden you have the ability to build entirely new categories of contracts. And that's really the outcome that we're seeking to achieve, is scale Ethereum in the sense that it can talk to all these inputs and outputs, and it can therefore be useful for all these other environments and use cases. Fundamentally, this means creating an oracle, a blockchain middleware, which I'm sure most of you here are familiar with the concept of oracles. And in the process of making these oracles, we've come to the conclusion that end-to-end reliability is particularly important. So the core concept is that if a part of your smart contract setup is insecure, then your entire smart contract setup pretty much isn't very useful to the customer. And that's why the reliability of oracles, so what we really want to do, we want to expand what Ethereum can do in terms of its capabilities to interact with useful systems, but we want to retain the guarantees of reliability and security that make smart contracts so useful. So fundamentally, we're just trying to make these two dynamics work together to scale what Ethereum's capable of, but retain security. Now, the fundamentals of our approach, which we'll go into more detail over this talk, and which we're thrilled to hear your feedback about, is the core approach is the same approach that Ethereum itself takes to secure the contracts. The core approach focuses on decentralization. So what it seeks to do is just the way that Ethereum has multiple node operators computing contract state changes, we seek to have multiple oracles that can compute the accuracy of an input, and we allow you to choose the degree of decentralization you want. So our system doesn't have a predefined amount of decentralization that somebody has to use. We allow people to scale up or down, that they want 3 nodes of a certain level of quality, or 5 or 10 or 50, depending on their need for decentralization and depending on their trust in each node in their oracle network. Now, the ability to make each of those nodes reliable basically comes down to a binding commitment. The binding commitment in our case comes through something called the service agreement. So this is an on-chain commitment by an oracle to a smart contract that it will provide certain types of data. And in a Chainlink oracle network, all the oracles make a commitment to provide this input. The larger the oracle network, the more nodes need to come to consensus, and therefore, the 1 or 2 or few nodes that deviate from the consensus, depending on the type of consensus you choose to implement, are generally considered wrong. And then they're penalized according to deposits and slashing and various methods related to proof of stake and these types of ideas. But fundamentally, that's the idea, is that just the way that smart contract state changes are made reliable, the foundational idea there, the foundational idea of our whole space, is that the security model of decentralization provides a greater degree of security and reliability for a certain type of data, whether it's a contract record or a state change or whatever it is. So that's fundamentally what we're basing this on. And then you also need the binding commitments between the contract and the oracle to be reliable. The third part of our approach is something called defense in depth. So the oracle software that we make is meant to be secure both on-chain and off-chain. So oracles are generally made up of two pieces of software. They have an on-chain component, which is commonly a contract that represents an interface which the requesting contract interacts with. And then you have an off-chain component, and the off-chain component is responsible for fulfilling the commitment that the on-chain contract made. And therefore for example, we've launched an Ethereum mainnet. Before we did that, we had 3 security audits, so that's securing the on-chain part of the code and being very rigorous about making sure that that code is secure and reliable so it doesn't introduce various kinds of attacks or vulnerabilities into the contracts that are using it or relying on it. And then the other part of making a good piece of Oracle software is securing the off-chain part of the code, and sometimes even securing it in a way that protects it from the node operator themselves. So even from the node operator running the off-chain Oracle software. So fundamentally, I'm just going to run through some of the logic of the initial approach for decentralization, and then we'll jump into a new approach we've recently launched called threshold signatures. Well, not cold threshold signatures, but our approach to threshold signatures, which has created, as far as we can tell, a 1,000x increase on the efficiency of how large Oracle networks can interact with Ethereum. So fundamentally, I think the way to view what the right model is commonly to think about what model we're trying to avoid or what failure scenarios we're trying to avoid. And fundamentally speaking, I think the failure scenario we're trying to avoid is one where you have a single centralized Oracle. Right? Because the fundamental promise of our space is not that there's one trusted third party controlling the entire outcome of a transaction. The fundamental promise of our space is that there's multiple independent node operators computing highly reliable contract state changes and storing that data in a way that everybody can rely on, so much so that they don't even need to keep redundant copies. Right? And fundamentally, if we build in some kind of singular trusted third party that can fundamentally control that transaction, that doesn't seem to coincide with the security model of our space, fundamentally speaking. So to solve this, I mean, it's basically the creation of an Oracle network. It's basically the application of decentralization to oracles, right? So if you have multiple independent node operators that are Sybil resistant, so they're independent, you have larger and larger numbers of them. Once again, the amount that a user feels they need, not some arbitrary amount that we force and dictate them to consume at large costs. And then once you've decentralized the Oracle and middleware layer, you can then go on to decentralize the data layer. So usually in our experience of building these smart contracts for large enterprises, together with various smart contract teams, generally speaking, the way this looks is, okay, we have decentralization reliability at this core smart contract state change level. Now we want to acquire it at increasingly outward bound levels. So that's initially the middleware, and then eventually the data provider, if you can manage that. This is an example of something called like a fully decentralized cryptocurrency derivative. So the way this looks is you have 3 separate data sources, completely independent of each other, feeding into 3 independent Sybil-resistant node operators, which are completely independent of each other, and they're arriving at a certain amount of consensus to provide a price input into a contract. And then this we have working on mainnet right now. If you wanted to go and use a decentralized Oracle network, you could get these 3 exact data sources, and you could have these 3 Sybil-resistant oracles give you the data to your contract for a higher degree of reliability and trust in the input into your contract. And then this Oracle network can expand to 5, 7, 21, 52, however many nodes the user feels they need. So that's another concept we'd be really thrilled to discuss, is what degree of decentralization in a collection of independent node operators is enough to provide a certain level of security. So we think this is another fundamental question of, is it 1,000? Is it 111? Is it 3? Is it 21? How many node operators do we feel independent Sybil-resistant node operators do we feel we fundamentally need? Then Chainlink, our approach, fundamentally what we do is we have deep integrations with data sources and payment sources because eventually I think the logical thing is that the data source themselves actually runs the oracle, and so that eliminates a hop. That eliminates another level of risk. So fundamentally, our approach focuses on integrations with all these different inputs and outputs at a deeper level so that eventually they can be almost natively integrated into each input and output, which once again eliminates a lot of the risk because maybe you might not even need an additional hop to an oracle. Then you just have to worry about multiple independent sources that run their own nodes inside their own environment. So I think what all of this will lead to is contracts like this where you can get various types of data for proving that, for example, goods arrived and that they were insured correctly and that they ended up at their desired destination. And fundamentally, I think that's really the outcome that we're trying to create. And then they obviously need to pay, so that's another key outcome. Now I think what we're going to do in the next part of the talk is I'm going to hand it off to one of my colleagues, Alex Coventry, who does research with us at Chainlink. And he'll describe an approach to making threshold signatures more efficient. And what that means is that now, basically the approach provides a way for there to be Oracle networks made up of thousands of independent node operators, but for their output to be verified on chain at an extremely low cost. So we've taken the cost down from something like, I think it was $3,000 per verification to something like $1.50 or less. So it's orders of magnitude improvement. And I'll hand it over to Alex. And when he's done, I'll come back and talk about TEs and defense in depth.
Yeah.
Grab this, thank you.
How do I operate this? I see. Okay. Hi everyone. So yeah, I'm going to tell you about threshold signatures. Let me just briefly explain the problem that we're solving. The obvious way to set up a decentralized oracle is to have each of the oracles sending in a report to a smart contract. So that's a separate transaction per oracle.
Can you speak more to the microphone?
Oh, sure. I've got a picture here. All right, great. If we can instead arrange an off-chain negotiation protocol between the oracles and then use a threshold signature on the observation that they all agree to, then we can then all we have to do on chain is verify this one approval here. So essentially what's going to be happening now is some new data is going to be coming into all of the oracles. They're going to discuss amongst themselves what the consensus observation is. They're going to construct a single signature between themselves, and then they're going to send that signed consensus data to the blockchain. The way we do that is with threshold signatures. So we're going to have n oracles, and then there'll be some threshold number t of oracles which need to participate in order to construct one of these signatures. This is not magic. This is cryptography which has been around since the turn of the century. But if you're looking for a friendlier introduction, this blog post explains it all the math in detail. Essentially what we're doing by doing this T of n signature is we're assuming that at most T minus 1 of the Oracle participants are dishonest. And so then because we require T signatures, we know that the value that they're signing has to be honest. The way this works is these n oracles collaborate to construct a public key P, which is the generator on the curve group times x, which is a secret which nobody knows. They all have shares of this secret X, which they can combine to do cryptography with this, but they can't. It would take T of them to actually reconstruct the secret, and we know that we're assuming that only T minus one of these participants are dishonest. And so then they use this long-term signature to sign a message. So essentially they go through the same procedure that they did up here to choose a secret K, which is called the nonce in a signature, and then a public value associated with that, which is just little k times G. Whoops. And then finally, what they share with each other is their bits of the Ks minus a challenge involving the message times their bits of the secret. And then from that, they're able to this signature, which is the secret K minus X times this challenge. And then this public K, the value S that they've reconstructed, is the actual signature. So this formula for the signature, it's linear in K and X, and that's crucial to the reconstruction process. It uses Lagrange interpolation, which is a linear process. So we're really depending on the fact that we can take linear combinations of the K's and the X's in order to get the secret K and X. But in this case, we're taking linear combinations of a difference between these, and that's illegible. So you can't actually reconstruct K or X from this. Now, this is a different signature scheme than Ethereum uses. Ethereum uses ECDSA, and the cognate to this S expression that I was just talking about is this for ECDSA. So in this case, it's nonlinear in K. We take the inverse of K, and that means that we can't use threshold signatures in this way. Now, it is possible to do threshold signatures with ECDSA, but the math is way more complex, involves much larger message space sizes. In theory, you could hold people to account in Solidity to make sure they're behaving correctly in this procedure, but it would be hugely expensive. So it would be much nicer if we could do this with Schnorr signatures, and Schnorr signatures, this linear property, gives them a lot of other nice opportunities that we may be able to use. So let's look at what we would have to do in order to verify a Schnorr signature on chain. Essentially what we do is we take the S in the signature and the K in the signature, and we compute this. S times the generator of the group plus this challenge times the public key. And then in secret, if you know what K and X are, that adds up to this, which is just K times G, which is this public K. So there's this sort of magic process where I give you K and S, and you calculate this, which has nothing to do with elliptic curve arithmetic, and you get back K. So we just have to check that the value we got is equal to K. So it comes down, the most expensive part is computing these scalar multiplications of curve points and an elliptic curve addition. So there is already an implementation of this using the pairing curve in Solidity with the precompiled contracts on the AltBN 128 curve. If you're interested, you can see that implementation here. Go to Harry R. Sol Crypto GitHub repository. It takes about 85,000 gas, sorry. Whoa, what happened here? Oh yeah, that's right. Yeah. Okay. So I don't know if any of you saw Vitalik's EC recover trick. He had a post on ETH Research about it. So essentially what you do is if you have a message hash and an elliptic curve point represented like this, and the scalar part of the signature, then when you compute EC recover, essentially what you're doing is you're getting back the Ethereum address of the curve that you get by calculating this arithmetic. Here, Rx is the x-ordinate of the point on the curve, and V is the parity of the y-ordinate. So we can actually abuse this to compute Schnorr signatures. And how much time have I taken? 5 minutes? Okay, great. Yeah, so we can actually abuse this to compute Schnorr signatures. So what we're going to do is, in the Schnorr signature, we're going to replace this challenge message where we take K and concatenate it with the message and then hash it. And instead, we're going to take the address of K and concatenate that with the hash of the message and then hash that. And then the signature is going to be this S, the same sort of S as we had before, but with this new challenge value, and then the address of K. So the address of K is just the 160-bit, lower 160 bits of the hash of the point K. And so essentially what we end up doing is if we go back to this slide here, we want to compute this and check that it's equal to K. Now instead what we do is we're going to compute the address of that using EC recover and then check that that's equal to the address of K. And so it turns out that if you plug this into the formula for EC recover, that should, on the happy path, that gives you exactly the address of K. So this is the check that we need to do now. So this returns a 160-bit hash. If you know anything about cryptography and hashes, you might be worried at this point that I'm opening myself to a birthday attack, which would only take 80 bits because of this 160-bit hash. But who's familiar with the birthday paradox? Okay, so in the birthday paradox, you have a room full of n people, and then you ask what's the probability that some pair in that room has the same birthday. And because there's roughly n squared possible connections, possible pairs, the probability increases. The probability of finding a collision like that increases with the square of the number of people. And so that's how a birthday attack works on a hash. Oh, my slides were cut off. Can I type somewhere? Because I can download my slides.
No, I have the slides.
Okay.
Maybe notepad.
Notepad? Yeah. I don't even have a keyboard here, so.
Oh,
There is a keyboard.
Oh, there's a keyboard. Oh, okay, great. Oh, no, that's not what I want.
Yeah, it shows the ATT. It's fine.
Oh yeah. Could you bring up the? Thank you. Thank you. That's great. Oh, damn, it looks like it got cut off there somehow. I will just bring up the, here we go. Control L. Oh, that doesn't work in Internet Explorer. Okay, here we go, web.edu/Alex.
So yeah, it says that there's only 8 pages.
I must have cut it off, or Google must have cut it off somehow.
Beyond it.
Okay, great. Sorry about this. I don't know what happened there. Yeah, okay, great. Yeah, so,
By the way, you have 1 minute left.
1 minute left. Okay, yeah, so this is essentially just going over what I just described, working out the algebra to show that what you get when you compute that EC recover is the same. So how do I go back on here?
On your keyboard.
Yeah, but it's, there we go, great. Yeah, so the other thing I want to say about this, there's no birthday attack because the things that you're comparing, they both have K on each side. So you can't pair arbitrary hashes to each other. You have to get the one with K in it on this side and then one with K in it on this side. So you actually get 160 bits of security from this. And if you're interested in this, this argument is made in more detail in this paper, Hash Function Requirements for Schnorr Signatures. Okay, and...
Your time's almost up.
Okay, great. So yeah, I have an implementation of this. It works. I've got it down to about 13,000 gas. In theory, I should be able to get it down to a marginal cost of about 7,000 gas per signature. That's it.